Hey, and we continue. So the first day is almost finished, and we have one speaker left. And I'm very glad and excited to invite to welcome our lovely and famous speaker Matvei.
Hey.
Well, some virtual applause to you. And
thanks.
Yeah, and I want to ask you just one small and very maybe controversial question. What will you prefer, imperative or declarative programming, and why?
Well, that's a very interesting question, and it's actually not an easy question. That's why it's kind of like I have the whole presentation about it. So the TLDR is I prefer both. I like declarative, but imperative is also important for many cases. So we can actually start and dive in, and I will explain why both are important, and it's actually very interesting relationship between them. So hello, welcome to my talk. As I said, my name is Matvei Malkov, and today we will be diving into the history of the declarative UI framework, what they were before, what is declarative, what is imperative, etc. So as this is kind of like a history lesson, we will talk about a few things. So first, we will talk about what were yesterday. So like, what's the history behind all, like in the world, declarative and declarative languages and frameworks throughout the history of programming. And then we'll talk about today, how we write today UI in Android, and not only in Android, like in web and everything. Then we'll talk about tomorrow, and we will see like what problems do we have today and how we're solving them today and tomorrow, and how we can build the bright future tomorrow. And then we'll talk about this particular bright future, and we will briefly touch Jetpack Compose and see how this bright future works in a real life use cases in Compose. So yeah, that's kind of our journey today. So let's start from yesterday. Actually, coming to the question that Pavel asked me, like, is declarative better than imperative? And people usually compare declarative, imperative is better, etc., etc. The cool part is actually they're not like it's nothing about what's better or worse. It's actually about the declarative is a very nice abstraction on top of imperative, and here is why. Let's to understand this, let's dive into the definition of declarative. So this is like a Wikipedia long definition, but the idea is you writing in declarative programs, you say what you want to achieve and not how to achieve this. You're like, here is what I want to have as a result, right? So in kind of like modern now, like Kotlin, Java, this comparison, it might look something like this. Like in imperative in Java or Kotlin, you can say you have like some variable that changes, and then you loop in the array and sum up this stuff. On like a declarative, more fancy stuff, you say, okay, I want to reduce. What do you want to do? I want to reduce my list and sum all the items. You don't say like how to do it, like loop and sum to some variable somewhere. But that's very sophisticated. It's a very complicated example actually. So let's take something easier. So let's take this program, the simple one. A is 4, B minus 2, and our result is A plus B. The question I want to ask here to the virtual audience is this declarative? Is this declarative enough? Do we want some abstraction on it? Or like, is this imperative? Do we want something more declarative? Interesting question, and it's not really easy to give an answer. To understand whether it's declarative or imperative, let's dive into the history even more and see the generations of programming languages, like to the very, very beginning. The first generation is a machine level. So maybe this guy von Neumann who like introduced all this stuff. So the idea is 0, 1, 1, 0, and you kind of write this down on a perfect card or whatever it's called, and you get the program running. So take this example: A4, B minus 2, result is A plus 2, A plus B. Here, what it will look like on the machine level. So the question is this imperative or it's declarative? So if you compare it, it's actually quite imperative, right? Actually, the fun part here is that if you take a look at this, and this particular one, it's actually a mistake, because this instruction 0011 0001 means subtraction and not addition, and we want a plus b. This is actually a mistake. Let's fix it. Here we go. Now we have like nice and working program. The lesson is here is I wanted to showcase that it's very, very imperative if you compare it to just a plus b, right? You describing what you want to do with your processor, and what you want, how you want your processor to understand you by just applying not any operations but just bits. So it's very imperative, right? It wasn't enough, and people built assembly languages, which is a second generation. Actually, assembly language is a declarative language because it declares the commands on the processor, right? So you say add, and you mean addition, not subtraction. If you want subtraction, you say sub, right? So this is a declarative language compared to the third generation. Of course, it wasn't enough, and then people introduced it like third generation, which we're kind of like using right now, Kotlin or Java, A, B, A plus B. This is also declarative compared to the previous generation. So, and the idea is like generations wrap each other, right? We have like this higher language, higher level languages right now, right? Which are like Kotlin in some sense, and some other like, parts of Scala, etc., which are basically like do with, reduce and all other even more sophisticated, even more higher abstracted things. So the takeaway is kind of currently what we are talking when we are thinking about declarative. We think about just the new generation that abstracts the previous one. So now the fourth generation abstracts the third one, makes it easier to use and makes it more suitable for more sophisticated tasks, which means that you have to have less knowledge about everything in the world to do the same program that you were like previously having a very hard time to write. The examples of the fourth generation actually might include 1C, which is a very interesting language, right? You probably know about it. We have also R or SQL, or even regex is also a declarative language, and actually fourth generation. The interesting part is, apart from R and 1C, like SQL and regex and all other DSLs like React, RxJava, or Jetpack Compose, they are all not really like full Turing complete languages, right? So they are DSLs. They are extensions on particular languages, or they're very like domain specific. Why? Is actually because we don't really need fourth generation right now. Like fourth generation need to solve our particular small problems that we have, like UI or that databases queries. We don't need like the whole language that introduces something more than we already have in Java or Kotlin. And so that's the interesting part about the history. The takeaway here is declarative is nothing better than imperative. It's just built on imperative, just new level of abstraction that gives you slightly less control, but more power. You don't need to worry about low-level stuff. Why is it so? It's because actually we need programmers to produce the next step, right? We like someone has to explain to the processor or to a lower level language how to do it. So you don't have to do it. You can just say what you want to achieve. Someone has to write this reduce function or plus operator in C++ to perform this, processor operations and translate it to assembly languages. So that's kind of like a brief history to basically understand like where we are coming from, right? So all of this is just an abstraction. Let's talk about today, and let's translate like to the actual talk, right, about UI frameworks. So how we write UI today? Let's take a look at HTML, right? Because it's an Android track in Android conference and mobile conference. Why not HTML? So if you take a look at HTML, what it has, like it has like .html file, and this is a markup language. So you just say what you want to see on a screen. Like you say div, list, div, paragraph, text, bold text, italic text. So it's very, what the HTML engine does, it just builds a tree and shows it. The tree is represented on the right. So in this sense, HTML is very, very declarative language. You just, say, I want to declare this on the screen, and that's all. But kind of like the interesting part is that it takes no input. So we kind of can describe it that it's a HTML engine it executes the function without any parameters and produces you a tree. Then you have to manually update, which will come back in a second. So yeah, this is the interesting part about it, is that if I change the title name from HTML to main layout XML, or whatever name you have in your Android application, nothing will change. So in Android, we have pretty much the same thing. We don't take like view binding or anything like this in our picture right now. But the idea is you have the same thing. You just just say text view, image view in linear layout, in constraint layout, and that's all. You don't have like a control over how it will change. You just say, here is my screen. The problem is that we are not in 1995 or like not even in 2005 or 10 anymore. We don't write static screens, static pages, static subscreens. We don't even have like static views. Everything is like animating, and you don't really want to reload the whole page when you click on a button or on a link. So we have dynamic UI right now, right, in 2020, which complicates UI quite a lot. Here's why we have like all these problems that we have in dynamic UI. Here's why like the mobile programming becomes so complicated nowadays, right? It's very interesting, very challenging part of our job to write UI properly. So dynamic UI, what it is, again, let's just specify what is dynamic UI. Dynamic UI is like when is a situation where you are in a state A, meaning you have some state on a screen. Then some event occurs, maybe from the business logic, maybe it's like push notification, maybe something else, maybe a user presses something. And then you need to perform a set of operations, maybe even with animations, and then end up in state B. Here's what I mean by dynamic UI, right? So you not reload anything. You just translate one state into another, maybe show some other button, or launch some animation. The example can be like this. You have 100 unread messages, user press, read all. You read all the messages in database, like send request to your server, remove the button, change to the green, the text. Like regular UI that you can write. Here is how it will look like, right? The dynamic UI in Kotlin. You just find a view that you define somewhere in XML, which is like very declarative, right? But it doesn't accept any state. So you have to like perform changes on it manually, set visibility to gun on one thing, or if if read count 0, remove thing. If read count more than 0, make it visible, change everything, change this color, etc., etc. It's not only Android problem, as I said, right? We have the same in JavaScript. In JavaScript, you can produce some HTML, and then you have to get element by class via jQuery or whatever, and then change it. It's very fragile. Why it's fragile? Well, the thing is, you have many states. You don't have state A and state B. You have state A, B, C, D, E, F, G, and then you have transitions between all the states. You can jump from one state to another, from A to B, from A to D, from D to B. And the problem is you can be between states, right? So not like we're not writing ideal applications where you have all of the stuff happening atomically somewhere in one place. Well, ideally. But sometimes you're in the middle of transition. You change one thing, you change another from A to B, and then you have to go to state C. And if you're not following me anymore, that's totally fine, because it's a very complicated thing. And you don't really want to think about it. So let's talk about how we can solve this problem, how we can make us not think about it at all. So let's build our new UM framework right now, right here. What we can do what if we will make our markup like HTML or XML aware of the data? Then we'll be able to specify UI is a function of not from nothing, but from state of your application or of your screen. Then we will allow you to build this markup that just specifies the state of your screen given this given the state, right? So like the idea is you specify how your screen will look like given the state that your application is in currently. So, and in our framework, because we will be aware of it, because UI is a function of state, we will be able to remove it for the user, meaning like for you, right? When you're writing an application. So let's try to build this kind of framework. So the idea is we will building this declarative framework on level 4 based on a level 3 generation. So 3 generations of markup and dynamic, and we are building it together on level 4 like a dynamic markup. The real example is React, right? It combines HTML and JavaScript to React components and JS6, if you know what it is. Same in Jetpack Compose. We combine XML and Java or Kotlin, actually Kotlin, to composable function. Here we're talking about this composable function, so I really want to describe what it is. Given the same example, you have this unread messages. Here is how it will look like in views, as we discussed, right? In dynamic UI in a 3rd generation of UI frameworks. Here, how it will look like in Jetpack Compose. So you have this unread section. As I said, UI is a function from state, right? So here is what we have actually. You have your function unread section that takes state as a count, and then you're able to use this state to describe your UI. You can say, okay, you have like count unread messages, then you're able to specify the color based on a count, and then if like count more than 0, show the button, right? If it will be 0, button won't be shown. Sounds very nice, right? You don't need to see like from what state you're coming from to what state. You just say, okay, I have this state. I don't know where I was before. I don't care about it. Here is how my UI should look like. Very nice. The question is how we can do it, right? So we have these 2 UIs. When count is 100, one tree. When count is 0, the other tree. The question is, here is like how they can be represented, right? Here the question is how to translate between these 2 trees. That's the very tricky part. This is so far the only kind of like tricky part of our framework, right? Aside from the rest. As I said, swapping the whole screens is very expensive. Otherwise, we will be all doing this, right? But we can start the whole screen of views, or the whole HTML page. Is very expensive and very laggy. You don't really want this. You want also maybe have some animations, move something around. So what if we will have the following idea? What if we will build virtual, cheap-to-use version of real UI hierarchy? And then if state changes, we build this new virtual copy, which is very cheap. And then we calculate the difference between these 2 copies and apply this difference as a sequence. It's like we will basically do the changes in UI for user, right? We will do like this view gun, view visibility, set color, etc. in a framework. So here how it will look like. We have like UI when your unread count is 100. Here's like, the dotted is virtual representation. The one on the right is real representation. So state changes to 0. What we do, we construct the new tree, new virtual representation. It's not tree. It's like just virtual representation. And then we calculate the difference between them as a set of operations, right? So we have this pseudo log, which says remove first child on the root. We remove it, create new leaf. We create it, and then we assign new leaf as a first child of the root. Here we can construct the log of how to go from state A to state B for you. You don't have to do it. The interesting part is that I said like it's just a virtual representation. It doesn't have to be a tree. So you can have like virtual representation 1 and virtual representation 2. So it can be anything, and you don't need to care about it because it's all under the hood. Again, so okay, we kind of like narrow this down to the smaller problem, right? The smaller problem, how to construct this set of operations on a real tree. And this is what all UI frameworks call reconciliation. So the problem, overall, what is reconciliation? The task is to build a minimal set of operations to go from tree A to tree B in our UI. The problem is the state-of-art algorithms to do it, like the real life algorithms that are proven to be successful, are very, very time-consuming, right? They're like cubic complexity, which means that it's very hard to do something reasonable in a reasonable time in UI, so users won't wait or see junk on our screen. Here is the QR code to the algorithms I'm talking about. So all of us know that if you want something to be faster, you need to build a cache. So let's make assumptions and cache things, right? The two interesting parts. If we can understand if that the element is the same, we can update the subtree and not to recreate the whole one, even for virtual representation, right? And the second part is if we can understand the item is the same and also all the parameters that it takes, because UI is a function of state, right? If the state is the same, the UI is the same. So we can be able to cache this whole stuff and produce the set of operations for a linear time, which is way faster than cubic, right? And it's actually proven to be good enough in many frameworks and in Jetpack Compose as well. To sum up a little bit, so we are able to build a UI framework which allow us to set UI as a function from state. So for developers, we can encapsulate state transitions, so they won't be able to, worry about it. They don't need to worry about the transition from A to B. But for us, we can perform for them, for developers, these transitions very fast, optimally, using this reconciliation algorithm. Right. So, and now we go into the super bright future when we are talking about Compose and see how we do it under the hood in Jetpack Compose. So here, basically, we kind of we are done. I'm done with my presentation, right? Kinda, because we already know how all declarative frameworks work. React, Compose, Flutter, all of this is just a basic definition of the new declarative UI framework. There are many other features, but this is the idea. This is the core principle that all UI frameworks, all declarative UI frameworks are powered by. So let's take a look under the hood of Jetpack Compose, shall we? This is the star, right, under the hood. Why? Because for now, the rest of 7-8 minutes, I'll be talking about implementation details, and they are subject to change, and you don't really, you won't really notice it because it's an implementation detail. The API will stay the same. It's mostly just for your interest to see how we are doing this reconciliation and everything in Jetpack Compose. We have to understand a few concepts before we go forward with Jetpack Compose, which are very important. First is the positional memorization. What it is, so let's build a UI in Compose. It's like a simple item. We take name and surname. We calculate something based on a name and show it as a text, right? Like Matvei Malkov and some data, maybe my card number. So the idea is we have these composable functions and composable function named remember. What remember does, it allows us to create kind of a cache based on the parameter. So here we say remember against the parameter. So remember that in this parameter, we have this calculation. So we are able to associate name with this calculation. And it's actually not even, remember is a small building block. And most of the composable functions behave the same. So here is the same idea. Text is relying on name, surname, and name date that we just calculated, right? So these three things are responsible for the invalidation of text. So we're kind of remembering the whole text, which has its own implementation based on these three parameters. What it gives us when, for example, surname changes, we're able to go to name, see that name doesn't change, and we don't need to perform this calculate data from name again. Maybe it's complicated, maybe it's big, maybe it draws some UI, maybe it changes some UI. We can skip it, right? Because we know that the name is the same. Name is the same here as well, but the surname is dirty. So we need to, therefore, recalculate the whole text and go underneath and recalculate text. If surname will be the same, we won't need to change text anymore because all the parameters are the same, meaning that the text is the same and UI that represents this text is the same. The fun part about it is that why it's called positional memorization is because we memorize by position. If you have the same remember call twice, there will be 2 cache entities, right? Because you can have like some other calculation based on it, and and basically like the part of this cache is where this call is. As I said, like most of the functions are composable functions, behave the same. Like we remember it, right? So if you have my app with item Matvei Malkov, for example, which is my name, by the way, we have the same. You have like this cache which says, okay, I know this Matvei and Malkov represent this item. And again, like if Malkov will change, we'll go through this whole situation in a cache inside. If we need to even invalidate item, then we go inside this remember, and then this text, blah, blah, blah. Oh, this is a very important concept, right? That gives us this like skippability, that gives us this linear reconciliation time, because we are able to skip some work and we don't need to redraw the like certain space on the screen, like this text or that image. We don't need to redraw it because it doesn't change. So let's take a look at how we store virtual representation in our in Compose. So we have this gap buffer. I said it's not a tree, right? It can be any virtual representation. So this gap buffer is somewhat like a array basically, but it only has one gap, like one empty space at all time. It can be very big, very small. We can increase it, but there is only one gap. So the fun part is we can perform several operations on it, right? We can insert items at the start of the gap, right? We can reduce the gap at the start and insert something. We insert more things. And also we can invalidate, right? We can jump to some position in a gap buffer, update. It's all like constant operations, by the way. And we can also move the gap. So this is the very interesting operation. This is the only operation that is not a constant time. So it's kind of expensive, right? So we can move the gap, and then we can insert more, like in between the items, right? And then we can extend the gap, removing something from below it. Which is also a constant operation. So the only expensive operation is gap move, which means that, okay, like we need to insert somewhere in the middle of UI, and the rest of the UI below probably is not worth anymore. So we need to clean it up. So it's all like, very not really applicative to real use case. So let's take a look at the counter. So this is like a button. You click it and then count 1, 2, 3, 4, 5, 6, 7, 8. So actually, let's take a look at what Composable does, this annotation. So we do some magic in compiler runtime and in this compiler plugin that we use in Jetpack Compose. And here is how actual code will look like that is running on people's devices. So we have this composer thing, which is basically a reference to the slot table. So you're able to use the slot table if you have this composer. Then we have these keys, and see the keys are different on the position. So basically, we can generate the key by the position in a code where this call is. So if you have two similar remembers, they will have different keys. And we have this start key and end key, which we will take a look at why we need it. But we take this key from the counter itself. So we have this gap buffer, and we can put stuff in it, right? We can say like, okay, I put key, and then I put this key, and then I put mutable state off, and I understand this mutable state off goes directly after the 1 to 3. And then we store the rest, right? We store 4, 5, 6, we store the text and on click, all basically the input parameters. As I described in positional memorization, we just put all the parameters and then we put the thing itself. For example, button can have like arbitrary implementation. We don't care about it. It will be like just bigger slot table. As you can see, basically we described here the whole our UI. We have this whole thing, which is a counter. We have this remember state. Then we have this button. And in button, we'll have the same, like parts of it. Let's see how we can update it. So basically coming back, this is how we store your UI, right? This is our virtual representation of the whole screen. It can be very big, but here how we store it. Kind of compact though. So representation update. how we can update it right now. It's kind of the same as I explained in the positional minimization part. Let's just take a look, right? So, for example, new title came. So it's not like I want to leave the same amount of count, 1, 2, 3, 4, but then title updates. So I see the same key, and I see the same 1, 2, 3. So this I skip the recreation of my state. My state stays the same, right? Because of positional minimization. Then I go to this key 4, 5, 6. I understand the button is the same, so I don't need to do anything with it. I see the title. The title changes, right? And the lambda is not changing because it's the same lambda, but title changes. Therefore, I have to reinvalidate the whole button and go inside and see what changes inside, because only text will change, right? Not the color, not everything, not anything else, just text. And here how we can update all the stuff. So for now, we were not really using 1, 2, 3, and 4, 5, 6. So let's see how we do like conditional logic and why we need it. Assume you have this kind of UI. You have feeds, and if feed is empty, you say, okay, no feeds, no new chats. And if there are any chats or any like news feed, you show it. So here, how we will expand it with our Compose runtime plugin, and we will generate 1, 2, 3, and 4, 5, 6, for example, and they will be separate because there are separate if and else statements. So what we will do, first the list is empty. You will put 1, 2, 3, you'll put text, and we are done. Then the new value comes, and we are going to else branch now, and we see 4, 5, 6, right? 4, 5, 6 is not equal to 1, 2, 3. So we move the gap, we remove the rest because we don't need it, right? Like it's a new UI, it's else branch. And then we put 4, 5, 6, and then the feed list. Here, how we produce the logic of condition. The same like for loops, right? We can generate keys, or people can supply us keys, and we can in for loop also understand what's moves and what's stays on the same place, what's removed, etc. We're kind of running out of time, but this is like the high-level idea of what you can do if you have the full control, right? If you control the whole hierarchy, if you control how your hierarchy is represented, you can optimize a lot of things, and you can do a lot of different stuff with users' UI, right? You can optimize it, you can provide them with fancy APIs. That's why like we have some interesting APIs in Compose, or in React they have a very nice, interesting APIs to allow people to build UI even easier. Or we can even do some observation optimization. So you can we have this mutable state that is like a arbitrary concept that again we don't have time to talk about now, but you can take a look how it works in our code base in documentation. The idea is like you kind of can redraw only the sub tree of the whole tree, so you don't have to go through the whole screen again. Very advanced stuff, very interesting, very allows to very nice optimizations. Or potentially we can save hierarchy in a storage. You have this like whole array. Why not store it somewhere and preserve for example, server-side rendering, right? We don't have it in Compose yet, or we won't have it maybe at all. But the idea is possible to build it, right? Because you store and you're on because of these virtual representations, you're able to have the full control, store it, restore it, maybe even make some changes on the server side, and then push it to the client again. Something like this. So we come into conclusions of our history lesson today. The very important takeaway is, again, declarative is nothing better than imperative. Declarative is just an abstraction built on imperative. Not everything is possible with declarative, right? So sometimes you have to drop down to the imperative level, and that's totally fine because they're not enemies; they're friends. Declarative is like a kind of like a child of imperative, if you prefer. So declarative UI frameworks nowadays, like this fourth generation, high transition between states. And this is like their main benefit for you as a developer, right? They allow you to set your UI as a function from state. They make it UI very easy to reason about and not worry about states. And they have these transitions between states under the hood very, very, very fast, or they try to be very fast at least. So yeah, you can do important things and not worry about the transitions, but also understand how it works under the hood. And so here's like where you'll probably listen to my talk. Slightly, if you want something more, we have this Compose main page with QR codes that we will show later. We have code labs that you can go and just nicely follow the code lab and see how to use Compose. We have a bug tracker. If you face any issues, please file bugs. We are very good at triaging them and very good at fixing, because we're like in a very active development stage. There is a in Kotlin Slack, there is a Compose channel. I really encourage you to join. We, like many developers from Compose, answer there. And also, there are many enthusiasts who are happy to help you with any questions or, any feature requests that you have. And with that, thank you very much. And this is a question and answers time.
Yeah, thank you, Matvei. It was very nice and it was very informative.
Thanks.
Good, thank you. Yeah, we almost ran out of time. Like we have.
Yeah, sorry about that.
Yeah, no, it's okay. I think that this topic takes time because it's quite complicated and very interesting. So we have about 4 minutes for discussion for the QA session, and there is one question in our Q&A section. So you can open it, and but I will read it just to see that everything is on the same page. What could be some limitations of declarative programming in general?
Oh, right, Stavro, this is excellent question. So I briefly talked about the idea is like declarative is, again, like is just an abstraction, right? So limitations might be like performance-wise, right? Because sometimes you really want to have the full control of all the optimizations. You really kind of going down the level to control all the stuff. So for example, a drawing, right? So we can build, I don't know, checkbox or something else with the higher level abstraction, but we really want low level like primitives like checkbox to be very fast. So we're going down the level and we're drawing it on a canvas still. So canvas is nothing declarative, right? Canvas is just draw rectangle, draw circle, move the canvas like 5 pixels. So this is kind of like the ideas where you can use it. Or for example, again, it's not only about drawing, like you can go down to the pointer input level and specify how you really want to pointer events to be interpreted in your system. Or like not even in UI example, so declarative programming in general. For example, C++, if you consider it declarative compared to assembly language, like C++ has inline assembly, right? Because sometimes you really want to go down and really want to operate on the assembly level to be very performant, because it's C++, you won't, probably, you're doing some microcontroller programming or etc.
Okay. I think that we answered. But yes, there is like if you want to get more details about that, so you can chat you can chat it in the chat. So yeah, okay. And there is another question: what do you think about dialects in Compose?
Thank you, Yulia. What I think about that, I think dialects in Compose, they exist. We are kind of like working on them. There are like few features missing, but in general, it's possible. Dialogues are like we do the dialogues in also like declarative style. So it's basically like, you have like, if I need to show my dialog, you just place the dialog and we show it. So it's nothing imperative. So we're trying to do a declarative way, and yeah, so far so good. If you face any issues or anything, let us know how it's going with dialogs in Compose.
Yeah. Okay, great. We have almost like 40 seconds to go to the close event of the first day. So I want to thank you once again for the great presentation, for the great topic, and for your details and everything. So yeah, everything was fine, and I will end session right now. So yeah.
Great. Thank you very much for listening. Thank you very much for hosting me.
Yeah, there's, yeah, okay, yeah.
Drop me a message and I will answer everything that you want.
Yeah.
And with that, have a good day.
Thank you. Thank you. Have a good evening as well. Bye.
Bye.